Okay, so Sparse LBL, welcome. By the end of this session, we're going to know what Sparse LBL is, and we're going to understand the performance and the limitations of Sparse LBL. So they're not necessarily limitations, more fine-tuning the system or understanding the best way to have these systems running. Okay. So what do we mean by Sparse LBL? What do you think? Before I go and tell you, and we go into a bit of detail with it, what do you think I mean by Sparse LBL at this particular moment in time? Just put it onto the screen or into the chat. What do you think I mean by Sparse LBL? What is it? Anybody tell me? Clue is in the title a little bit. Anybody going to have a shot? Just a couple of words. Don't need to write anything big. What do you think it's likely to be? Using a partial LBL array. Thanks, Sebastiano. Yeah. Like LBL, but more sparse. Yeah. More than an LBL. More than an LBL. Actually, yeah, fewer than an LBL array. Okay, good. Right. So Sparse LBL. Probably a good place to start is with LBL, so the full traditional means. So we've got this on the screen here. We've got this full array, this pentagon-shaped array, probably a perfect array, the most perfect array you're likely to see. Good geometry, lots of redundancy. We've got 5 transponders and very good line of sight and all that sort of stuff. So a very good array over here. This side, we've got a square array, 4 transponders, but we've still got very good geometry. Okay, but how do we calibrate these things? Just as a recap, how would we calibrate these two? Just one word or two. How would we calibrate these two? Anybody got anything? No answers? First geometry of the array, then box in. Okay, yeah, thanks, Sebastiano. Yeah, so what you mean by geometry of the array? Somebody else has put box in on the screen. Yeah, what you mean by geometry of the array is, I guess, some kind of relative calibration. So Tom's put there, baseline relative cal. Excellent. Right, so we're going to take baselines between all our points on the seabed here. Same over here. We're going to measure the distance between them. We're going to feed that into a piece of software. We're going to mathematically adjust where they all are based on the range that we've measured, and that'll be it. So that's what we'd call a relative calibration. We're also going to tie in depth somewhere as well, obviously, for 3D positioning. Somebody's putting box in, and a few others put box in into the chat. Yeah, we would also box in. So potentially these two here. The reason we do these two here is obviously the longest baseline. The reason for doing the longest baseline, as we talked about in the LBL webinar 2 weeks ago, was to constrain the orientation of the array. If we just boxed in one of these, the array, when we did the calibration, it would be allowed to pivot or swing about that point. So by having another constrained point over here, we can constrain the orientation of the array when we come to do the calibration. Okay, so with LBL, just to continue the recap, once we've fixed these references on the seabed, we've got 4 transponders in this particular case. We've got good geometry. We've got lots of redundancy, usually, and in this case we've only got 4, but we've still got redundancy. And the rules of LBL always say that we need a minimum of 4 ranges to derive position. Okay, so in this scenario, we've got four ranges. We can position this vehicle quite nicely within that space. Okay, and obviously with an LBL array, as we talked about in previous webinars, we would be working within that environment, within that array. Okay, we couldn't move out here necessarily, or we could, but the positioning wouldn't be quite as precise. Okay, so we're working within the array with an LBL. So let's change that to a sparse LBL scenario. We've reduced the amount of transponders on the seabed. Now we've only got 2, whereas before we had the other 2 at the top. You may see it referred to as a sparse array. You may see it referred to as range aiding or hybrid navigation. Okay, they all mean the same thing pretty much. We're using the range information from subsea transponders in order to feed our INS on our vehicle. Okay, we're not feeding an LBL position to the vehicle, to the INS. So LBL does a least squares adjustment, whereas range aided INS, it will take the range information and then the INS will predict the position of the vehicle based on the range information in the Kalman filter of the INS. Okay. What have we reduced in this picture? The obvious answer is we've reduced the amount of transponders, but by reducing the amount of transponders, what else have we reduced? Anybody tell me? Redundancy. Thanks, Sebastiano. Yeah. Excellent. We've reduced redundancy. Okay, so we've got less redundancy and therefore our 4 range minimum is unachievable. Okay, so if this was just a typical scenario, we didn't have an INS, it was just an LBL scenario. If we only had 2 ranges, we wouldn't be able to position the vehicle because, well, we wouldn't be able to position the vehicle with any confidence because we haven't got enough ranges. Okay, you'll notice also in the picture, the position of these transponders relative to the vehicle, they're actually strategically placed in order to maintain geometry. Okay, so you can see we've got one out here which is to the side of the vehicle and one out in the forward aft direction of the vehicle. Okay, so this is what we'd call managed geometry. We've had to manage the geometry of the system in order to maintain the precision of the position of the vehicle, utilizing the ranges. But as I said earlier, we've added the INS. So I talked about this as just a solely LBL scenario, but because we've added an INS, oops. Oh, that's supposed to, sorry, excuse me. Because we've added an INS, we've got the short-term gain, the short-term accuracy gains of the INS. Yeah, it will hold its position for short periods of time, and that will be a very robust position. But longer periods of time, it starts to drift, as we talked about last week. We're combining that with the long-term accuracy of our LBL system, so our range system. So as we know, the environmental effects, the short-term effects on an acoustic system causes fluctuations in position sometimes. So by combining the 2 systems, the INS system and the acoustic system, we've got the best of both worlds. Okay. So short-term accuracy of an INS, long-term accuracy of the acoustic system gives us the best of both worlds. Is basically what I'm saying. Okay. So just to recap, something we did last week. Don't worry about this slide. There's lots of information on there. I completely appreciate that. The bit I want to basically touch on is this section down here. Okay, so this was where we talked about the way the INS works. So we've got our INS algorithm here, this bottom pink section, and this will produce a position estimate based on movement and movements of the vehicle. Yeah, it will predict its own position, and it will, when we get an observation from an observation such as a DVL or a USBL or something, it will compare that estimate that it's produced with the incoming observations. Okay. If the incoming observations agree with the estimate, then they're allowed into this error state Kalman filter, and then that will fine-tune the position estimate basically. So utilizing the observations to fine-tune the position estimates of the INS. So the thing I want to recap here is obviously this LBL section here. So for sparse LBL, we're using the range information from our subsea transponders. So this is the section we're talking about here. So although it says LBL, as I said earlier, it's not actually LBL, it's range aiding. Okay, so we're feeding the range information into the Kalman filter. The Kalman filter is then utilizing that range information in order to correct its position estimates. Okay, that's all I wanted to say about that slide. So don't worry, because we covered quite a lot of detail about that one last week. But I've also mentioned this term, managed geometry. So what do I mean by that? Let's have a look. In the picture here, I've got this ROV. It's navigating down a pipeline. We've got over here, we've got a subsea transponder, and then out to the side here, we've got a subsea transponder. Okay, so we're going to navigate down here, and we're going to collect a range into our INS from one range from the side, or from the cross-track direction. And what you can see in the picture is that the range is constraining the air ellipse in the direction of the range. Okay, so the air ellipse elongates in this direction because this is forward aft, this is cross track. Okay, so the range is constraining the cross track error. Okay, and the forward aft direction is also being assisted slightly by the direction of travel of the vehicle. Okay, so the Doppler observations, the DVL observations are in the forward aft direction. The INS movements are in the forward aft direction. So that is helping to constrain this air ellipse slightly in the forward aft direction as well. So the reason I'm telling you that is obviously when we started talking about this technology, this sparse LBL technology, we initially said you could potentially use it with one transponder. That is still the case. You could still use it with one transponder, but we've since actually said that it's better to use it with 3 transponders as a minimum, just for QC and also redundancy. Okay, and the reason being is obviously with one transponder you can see the dangers in the precision of position if you're only using one range. Okay, so your air ellipse is going to elongate in one direction based on the orientation of the range. Okay, so obviously your position precision is going to be somewhere within this air ellipse. So when utilizing one range in a sparse LBL side of things, then it is possible to change the geometry of the whole thing just by switching the heading of the vehicle. Okay, so in this case, this is actually the best scenario for utilizing one range because our direction of travel of our vehicle is in the perpendicular direction to the range, which means it's going to help constrain the air ellipse in both axes. Does that make sense to everyone so far? Just give me a tick or a thumbs up. Make sure you're all happy. Good stuff. That's basically what we're doing. We're trying to constrain this air ellipse as best as possible, utilizing the observations. Okay, good. Right. Let's take just to go a little bit further with that point. If the ROV was traveling towards this transponder, the direction of travel of the vehicle and the range would all be in the same direction, which means that the air ellipse would elongate quite a lot in the cross-track direction, okay, because everything is now in the same orientation. So let's have a look at that scenario. Let's take the range from behind this time. Oops, I know, stolen my sandwiches. Right, what I'd like you to do is get the tool, the tools that we used earlier, the circles, and draw the ellipse that you think we're likely to see here. So grab your tools and then draw the ellipse that you like to see. We've got one range from behind here, so what's likely to happen to the ellipse? Somebody draw one. I even gave you the answer by accident. Yay, thanks Asa. Yeah, and David, good stuff. Nelson, yeah. Excellent. Great ellipse, Nelson. Good stuff. Okay, so all exactly right. Yeah, it would be in this direction. Oh, Ace has gone a bit controversial there. The previous ones were all good. This one's a slight obscurity. Okay, so remember, Asa, the range is going to constrain the air ellipse in the direction of the range. So this range is coming from this direction. So we're going to squash the error ellipse in that direction. Okay, let's just clear those down and make sure you're all okay with that. Oops, oh my goodness, I've got mouse issues. There we go. Right, so that's what you like us to see. So the error ellipse elongates. You can see it's slightly bigger than it was before, and that's because our direction of travel of the vehicle with our DVL velocities and our INS movements are in the same orientation as our range measurements. Okay, but obviously with this type of system, what we're looking for is a nice equal error ellipse in order to maintain precision on the position of the vehicle. So let's take this scenario. We've got one out to the side and we've got one from behind. We are getting what's called a good angle of cut. So we talked about this before, angles of cut with an LBL system. We're talking about the same things with the sparse LBL system. So we've just got less transponders to do it with. So we've got this good angle of cut here between two transponders, not quite 90 degrees, but as close to 90 degrees as possible. So what's going to happen to the error ellipse here? Again, grab your tools, just draw the ellipse for me. This time we've got range from behind and a range from the side. So the error ellipse should do what? Excellent. Thanks, you guys. That's good. It equals out as best as possible. Okay, so this is what I'm talking about when I'm talking about managed geometry. Okay, so the geometry of this is actually very good, even though we've got less transponders. So the position precision is still maintained. Excellent. Thanks for the drawings. That's good. There we go. So that's what we're likely to see. Okay, so INS position uncertainty. We talked about this last week. The uncertainty of the INS position is constrained in both directions, basically, is what that's saying. So I think we've seen this picture before as well, but this should all make sense now, hopefully, if you understood that last bit. This is a pipeline survey. Let's imagine an ROV is navigating along this pipeline. At any point in time, it's going to get relatively good angles of cut from these subsea transponders. Okay, so one thing you'll notice is we've only got 3, so we've reduced the amount of transponders, but they're also all only on one side of the pipeline. Okay, so with a traditional array, they would normally be surrounding the pipeline. We'd have them all the way around in order to maintain geometry. But in this case, because we're using sparse LBL, we're combining our acoustic system with an INS. We can just have them all on one side of the pipeline, which reduces our overall deployment costs. It reduces our calibration time. It reduces the overall cost of the transponders themselves initially. So it's obviously a good thing for customers. So you can see now that you know, even if I was here, I'm maintaining this angle of cut between these transponders if I'm collecting the ranges from these transponders. And then at some point when I get up here, I'm going to start to collect the ranges from this one in conjunction with this one, and that's going to maintain my angle of cut again. Okay, so you can see based on what we've talked about with geometry, we can plan our sparse array accordingly, and you can see here we can spread them out quite nicely. But how does the geometry and the redundancy affect the position of precision of position? Let's have a look. So this is our in-house LBL planning software. And what you can see on the screen here is we've got an ROV. This is a full array in this particular case. And what it's doing is just simulating basically the ranges that you're likely to achieve as you maneuver outside of this array. So one thing different from LBL is we can actually navigate outside of an array. As long as we can collect ranges into the INS, we can navigate quite nicely. Okay, so we don't need to work in the confines of this array. Okay, you can also see some colors on the screen. So you can see it's quite blue. And if you look at the key over here, this is an indication of the precision of the position of the vehicle. Okay, so you can see the blue is the 0.00, and that's in meters. And then up to, as the redder it gets, basically, that moves up to ½ meter. Okay, so in terms of precision, in this particular case, even though we're outside of the array, we're maintaining very high precision. Okay, but let's reduce the array down to a 3 transponder array. So now we've got a sparse array. So I've only got 3 transponders. And you can see we maintain fairly good precision most of the time, as long as we're maintaining good angles of cut. But when 2 transponders are in line with one another, as you'll see in a minute, when we get down here and these 2 are in line, you'll see that the precision starts to degrade slightly. And that's because we've lost that angle of cut that we talked about earlier. It's actually helping a little bit because we've got a triangle. So we've still got a range out to the side slightly when it happens. So we're not degrading it massively, but it's still having an effect. And then what about 2 transponders? So this could be a typical scenario with a sparse array. It might be a series of compacts along the side of a pipeline. So they may be in a long line. Okay, there's no geometry. And you can see what happens when you go between them or out to the side of them. When they're in line with one another, look what happens to the precision of the position of the vehicle. It drops significantly down to about 1/2 meter. Okay, so this is one thing that some people tend to struggle to get their heads around initially with sparse arrays. And obviously, because from a traditional array, when you go between 2 ranges with a traditional array, that's usually a good thing, because you're getting lots of redundancy and you're getting ranges from both sides. But with a sparse array, that's actually the worst thing for the INS if there's only 2 compacts. Okay, good stuff. So is everybody okay with that so far? Everybody understand that geometry is incredibly critical? You know, even when we're planning these sparse arrays, we need to make sure we've thought about that angle of cut that we're going to get to maintain that error ellipse. Is everybody happy with that? Give me a thumbs up or a tick just in the participants tab. Good stuff. Thanks, Asa. You've put yes in the chat. That's good. Right. So why would we use this system? Yeah. Why are we going to use Sparse LBL? Let's take a typical oil field development. We've got lots and lots of transponders, lots of redundancy. What we may have struggled with initially was getting line of sight between them all, because we've got all these structures on the seabed. Okay, but quite a large array, lots of transponders, quite expensive. Yeah, we've got a lot of transponders initially, which is expensive anyway. We've got to calibrate them, and we've got to deploy them, which is going to take a long time. Okay, so let's reduce it to a sparse array. We've got less transponders, so we've reduced the cost straight away. We may have found it easier to get line of sight because we've got less points within all these structures on the seabed. Okay, so one of the main reasons and drivers behind this is obviously to reduce cost for the end user, especially in this day and age. Is one of the big drivers for most projects. And I guess it's going to be even worse as we come out of this particular scenario. They're going to be constantly looking for cost-saving measures. So this is one of those cost-saving measures: is to reduce the size of your arrays but still maintain precision. Okay, so all through here, it wouldn't matter too much that we're going to maintain precision. We could dip behind structures with our vehicle because we've got an INS on it. And it wouldn't matter that we lost line of sight to some of these transponders, because the INS would hold the position. Okay, we can also apply it to other scenarios. So in this picture, we've got 3 colors. We've got the green, which is this pipeline. So it's probably got a lake